All right, today's lesson, we are talking about section 5.3, inverse functions and their derivatives. The three objectives for today are talking about how to verify functions are inverses of one another, determine whether functions have an inverse, and then, of course, derivatives of inverse functions. So let's refresh our memory on inverse function. You probably talked about this last year in pre-calculus and probably the year before in advanced algebra. So an inverse function is the function when f of g of x equals x and g of f of x equals x. And then we would say that both f and g are inverses of each other, and the notation would be f with this little -1 exponent or f inverse. Okay? So to think about this visually, basically what's happening is I have a value x. It's in some domain of f, what we'll call set A. And then I take it to its output f of x, which is going to be in the range of f, which is set B in this picture. And then f inverse is going to take all of those values in the range and put them in the back to their inputs in the domain. So the domain of f is the range of its inverse, and the domain of the inverse is the range of the function. So that is something important to remember and something you're going to use continually when talking about inverse functions. So the notation for an inverse can be confused with a reciprocal. So make sure you're not confusing it with reciprocal. When we typically put an exponent between the f and the x in function notation, it doesn't mean an exponent like traditional use of an exponent would. So if you wanted to write this as a reciprocal using exponents, you would say the reciprocal 1 over f of x would be f of x all to the -1. So that's how we would use the notation there. The next thing we're going to talk about is the reflective property of inverse functions. And so if we want to talk about inputs and outputs, we can talk about points. So if AB is on my function, then BA is going to be on the graph of the inverse. And so when I graph all of those points, I see that the segment from AB to BA is going to be bisected by the line y equals x, and it's also going to be perpendicular. So the line y equals x is the line of reflection between a function and its inverse, and it's also the perpendicular bisector between two points that are inverses of each other. So pretty cool stuff, some geometry there. It's exciting. Okay, our first example. Let's verify that these two functions, f equals 2x cubed minus 1 and g equals the cube root of x plus 1 all over 2, are inverse functions of each other. So if I go back to the definition, it reminds me that I need to show, so I use NTS for need to show all the time, that f of g of x equals x, and I also need to show, you have to show both, g of f of x equals x, okay? Because they have to be inverses of one another. Okay, so let's get started. So I'm plugging the function g into f for the first one. So I want the cube root of x plus 1 over 2 into my function f. So 2 times the cube root of all of that mumbo jumbo cubed minus 1. So the cube and cube root cancel. So I get 2 times x plus 1 over 2 minus 1. The 2's cancel, I get x plus 1 minus 1, and then of course the 1's cancel, and I just get x. I'm going to let you try it the other direction on your own, and of course you should also just get x. Next, how do we know that an inverse exists? Well, the main thing we know for an inverse to exist is that our function has to be 1-to-1. So remember, the easiest way to check if it's 1-to-1 is using that good old horizontal line test, okay? So another thing is, if my function is strictly monotonic on its domain, then we know it's 1-to-1. So this is a special case, so they kind of gave it its own little thing because it's one of the easier ones to look at. So we have two examples here. Do the following functions have an inverse? So let's take a look at their graphs and see what we think. So this first function, and I don't expect you to know how to graph a cubic by hand, so it's okay if you're using Desmos or your graphing calculator to do these. Let's see here. So the x-intercept's -1, does not cross 1, and looks kind of the same on the other side. Okay, so there's my function. So if I look at it, it looks like it's monotonic because it's non-decreasing. So a good way to figure out if it's non-decreasing, well, let's look at the slopes. And our good old friend, the derivative, helps us with that. So the derivative of f of x, so f prime of x, is 3x squared plus 1. And when I look at that, that is going to always be greater than 0 for all x that are real numbers. Okay, new notation. I'm pretty sure none of you know this. Okay, so this upside down capital A means for all. And this little like euro looking thing means element of. And then we got our good old friend, the real numbers. Okay, so that just means that that's going to work for all of these x's that are real numbers. So any real number you plug in there, we know it's greater than 0. Okay, so it's just specifying where x lives for all the x's that are real numbers. Okay, next function is x cubed minus x plus 1. So if we graph this one, it has a y-intercept of positive 1. And it also goes through the point 1, 1 and negative 1, 1. And looks like something like this. So if I was to do my good old friend, the horizontal line test on this one, it does not pass. So, oops, I forgot to even put my answer for the first one. My goodness, I got so excited. So the first one does have an inverse. Okay, since it's monotonic. All right, this one does not have an inverse since it is not one-to-one. By the horizontal line test. Okay, and graphing it and showing me the specific horizontal line you picked that it does not pass is enough to show that it's not one-to-one. Great. Guidelines for finding an inverse function. So first we want to make sure one of them exists so you're not wasting time. Okay, so use the theorem we just talked about to figure out if it exists. The next two steps, you're going to switch x and y. You're going to solve for that new y value, and then you're going to put it back into the f inverse of x notation. So that's just your algebra part, steps 2 and 3. Step 4, you're going to make sure that your domain and range, so the domain of one is the range of the other and vice versa, so make sure those match. And then last step and final step, you're going to go ahead and do that check of that the compositions work both ways. Okay, so let's put this all into practice. So find the inverse function of the square root of 2x minus 3. Okay, so the first thing I want to do is make sure it has an inverse function. So let's graph this puppy. So I like to use transformations when I graph. So if I factor out that 2, I get x minus 3 halves, which means I have a horizontal compression by 2. And I also have a shift right by 1.5. Okay, so those are my two things here. So if I think about my original square root graph, I'm going to go right 1.5 units, and that's going to be where I start instead of at 0, 0. And then it's going to have the same general shape, but it's going to be a little squattier, I guess you could say. All right, so it's going to be something like that. Okay, so yes, we see that this is monotonic. Okay, you could take the derivative if you want to. You can just look at the graph. All right, so yes, we know we got an inverse to work with. All right, so now let's do the algebra. So if I write it as y equals square root of 2x minus 3, switch x and y, and then go ahead and solve for the new y. So I get x squared equals 2y minus 3. X squared plus 3 divided by 2 is going to equal y, or f inverse. Okay, so now we got to think about domain and range. So if I look at my original function has a domain. It starts at x equals 1.5 or 3 halves. So this one is for all x greater than or equal to 3 halves. So that's going to be my range of my new function. And we have a quadratic here. And so if I'm going to graph this one, remember that they are reflections of each other over this line y equals x, so that can help you think about how to graph it. So it's going to look like this. Okay. And so if I look at this, my domain is going to be for all x greater than or equal 0. Okay. So there we go. That is how that works. And and then step 5, verifying that when I compose them together, I get x. I'm going to leave that part to you because we already did an example of that. Okay, next, the derivative of an inverse function. Yes, derivatives. Okay, here we go. So let function f be differentiable on the interval I, and if f has an inverse function g, then g is differentiable at any x for which f prime of g of x does not equal 0. Okay, moreover, oh hey, here we have this cool formula. There is a proof for this formula in Appendix A. So if you are interested in how this came about, check out Appendix A, okay? But I would write this down in your notes. So g prime of x equals 1 over f prime of g of x. Okay, so how are we going to use this? So let's do an example. Let f of x equal 1/4 x cubed plus 1 minus 1. What is the value of f inverse of x when x equals 3? Okay, so if I want to figure that out, I'm going to say, well, I know when x equals 3, that's the input of the inverse, so it's the output of my original function. So I get 3 equals 1/4 x cubed plus 1, plus x minus 1. And you can graph that. You can solve that on Desmos. You can solve this on your calculator however you want. I solved it on my calculator. I plugged this into y1. And I plugged this into y2, and I found where they intercepted. And that was at 2. So I found that f of 2 equals 3, which means that f inverse of 3 equals 2. Great. Next question said, what is the value of f inverse prime of x when x equals 3? Okay, so this is where I'm going to use this handy dandy function here. So I know that f inverse, the derivative of that at 3 is going to equal 1 over, and then here I already have the function. Remember, g is my inverse. So if I look at my original thing as the regular function, and then f inverse of x. Whew. Okay, here we go. So then I get 1 over f prime of f inverse of x, and x is 3. I should write that down. Replace that with the good old 3. So we found that was 2. So I want f prime of 2. Okay, so what's my derivative now? Did we find f prime of 2? We did not. So f prime of x is going to equal 3/4 x squared plus 1. And f prime of 2 is going to then equal 3, because that'll be a 4. The 4s will cancel. 3 plus 1, which equals 4. So then I get 1/4 is my final answer. How exciting. All right, cool. I think that's it. Oh, no, we're not done. Sorry, I lied. Did we do all that problem? Yeah, we did. Okay. Reciprocal slopes. Okay, so if I look at this in a little bit more detail, the formula we just talked about, it's actually kind of cool. So if I think about it, I have that g prime of x. If we think about that as dy dx, then I can say, oh, hey, that is going to be 1 over f prime of g of x. Okay, which then is, well, what is g of x? G of x is y, so f prime of y. And, well, what is that? That's the same thing as dy dx. Dx dy, I'm sorry. And so that's kind of another thing you can think about, is that if I have dy dx, that's the same thing as 1 over dx dy. And so then the slopes of my inverses are going to be reciprocals of each other for the corresponding points. All right, so take some time, convince yourself that you believe all of these steps and figure out how they work. Refresh your memory on some of that notation for derivatives using primes and dy's and dx's and all that kind of stuff. One last example. So let f of x equal x squared for all x greater than 0, and let f inverse of x equal square root of x. Show that the slopes of f and f prime are reciprocals at 2, 4, and 4, 2, respectively. Okay, here we go. So if I want to talk about f prime of x, we get 2x, and so f prime at 2 is going to equal 4. And then if I want to do the other one, f inverse prime of x, man, that's quite a mouthful, is going to be 1 over, so 1/2 square root of x, because we get to the negative 1/2, great. And then when I plug in into that one, I'm plugging into 4. I get 1 over 2 times the square root of 4, which is 2. So I get 1/4, and they are reciprocals. So we are happy. Great. Now we are done with the notes. So go ahead.